Okay, now we're going to the negative binomial distribution. And for this one, it is a statistical experiment that has the following properties. This actually is kind of close to just the binomial, but you'll see that there's this odd little twist to it. We have the experiment has X repeated trials. Each trial has 2 possible outcomes. Sounds familiar. The probability of success is the same on every trial. They're independent, right? So this is sounding pretty close. About the only thing that's different before from the binomial is, remember before we had n altogether, but now we're just having X repeated trials. And the experiment continues until R successes are observed, where R is specified in advance. So we're looking at something that's pretty close to binomial, but not quite there. But I'm going to show you so you can see more clearly what we're talking about. Before I actually show you, I do think it's appropriate to write out the formulas so you know what we're talking about. And we're discussing a phenomenon where a trial number, we're looking for the trial number where an event A occurs for the kth time. Here's what I mean. I'm flipping a coin. I flip it the first time, and what I'm looking for is, I'm looking for tails. So I flip it, I get a head. I get a heads, I get a tails. That's the event I'm looking for, is tails. But I'm looking for where it occurs the 3rd time, say. So we go heads, heads, tails. Oh, that's the 2nd time. Heads, tails. What's the probability that it's going to take me 1, 2, 3, 4, 5, 6, 7, 8 times to get my 3rd tail? That's what this distribution, the negative binomial distribution, is all about. And so we can write that as the probability of X is equal to, and this is this binomial distribution, X minus 1 factorial. Where's the minus 1 factorial? It's like getting you to the distribution all the way up before you get the final thing that you were looking for. That's where that minus 1, and the minus is where that negative kind of falls out of. And we can say k minus 1 factorial times x minus k factorial p to the k and q to the x minus k, where 1 is less than or equal to k is less than or equal to x. Because you can't have like the, you know, if you're looking for the 3rd tail and you throw the coin 8 times, that'll work. But you can't like have 9 tails and you only threw the coin 8 times. That's what this is all about. So, and of course 0 elsewhere. Now we can say we're on any trial, P is equal to probability of A, and Q is equal to the probability of A's complement, which is just 1 minus P. And note that the order doesn't matter except on the last trial, X. So see, order only mattered that we got T on that very last trial. So it's kind of a funny thing. It's like most of the time order doesn't matter, but occasionally it does matter. Okay, oops. So never mind that. Okay, so the differences, let's look at the flat out differences between the binomial and the negative binomial. First, let's bring up our little mnemonic, you know, N2PI. So if we're looking at the binomial, does order matter? Well, no, it doesn't matter at all. From that perspective, we've got Bernoulli doing just fine, okay? Now, Does order matter for negative binomial? Well, yes, at least on the last one. But before that, Bernoulli does apply. So kind of gives you just a little perspective of what's going on and how the two different distributions look a little bit different, but are actually similar in many different ways. So let's have an example of a negative binomial distribution. Let's say we flip a coin, like we have lots of time on our hands, and we just sit around flipping a coin, and we count the number of heads, and we'll count those as successes. If we continue flipping the coin until it has landed 2 times on heads, we've conducted a negative binomial experiment. And the negative binomial random variable is just the number of coin flips required to achieve 2 heads. So you can see that tails, 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 heads. Now, to go for that last one, you can pretty clearly see that the more coins you throw, the tinier the chance is going to be that it's going to take that many throws to get that number of heads. So in this example, the number of coin flips is a random variable that can take on any integer of value between 2 and plus infinity. So you can see here, what's the chance we're going to get? Two heads on 2 throws of the coin? 0.25. It's also 0.25 for 3 flips of the coin. But then from then on, as you go higher and higher, the probability that it's going to take that many flips for you to get that second head is going to go down and down and down. And that's what this graph shows. So now let's reiterate the binomial distribution. Consider the following statistical experiment. You flip a coin, you count the number of times the coin lands on heads, you continue flipping the coin till it has landed 5 times on heads. This is a binomial experiment. Why? Because we've got a certain number of repeated trials, and we flip a coin repeatedly until it's landed 5 times on heads. So every trial has just 2 possible outcomes, heads or tails. The probability of success is consistent. We've got 0.5 on each trial, and each of these trials is independent. That is, getting heads on one trial doesn't affect any of those other trials. So that's a good example of a negative binomial distribution. Let's look at oh yes, and finally, the experiment continues until we get a fixed number of successes, and in this case it's 5 heads. So going back over just to make sure we're on the same page as far as notation goes, we can say, first off, the number of trials required to produce k successes in a negative binomial experiment is just x. The number of successes, well, you can guess it's going to be k. The probability of success on an individual trial, well, we've already seen p. We can use either a capital P or a little p. And likewise, q is the probability of failure. That's just 1 minus p. And then we can say that the negative binomial can be written as b asterisk with x and k with a given probability. So it's x trials, k successes with a given probability. Again, so it results in the k success is on the xth trial, when the probability of success on an individual trial is just p. And then, of course, we've got that combinatorial that we're used to seeing. That's the combination of n things taken k at a time. So the origin of the formula actually makes good sense. We can say the probability of getting some x right there is that we've got our event occurring so many times, it's k minus 1 times, in all the way up to the trial right before the very last one. And then on the very last trial, we also have that event. Okay, so that's those two events have to intersect one another. So that means we can multiply them together, and this part can be written like this: x minus 1 to the factorial all over k minus 1 to the factorial, and then we'll put x minus 1 minus k minus 1 factorial. Okay, and then we'll take p to the k minus 1, right, and q to the x minus 1 minus k minus 1, and take all of that, put it in a big bracket. So that is this whole thing, right? And lastly, we've got this part right here, and the probability that this occurs on any given trial is just p. So, okay, so we multiplied everything all out here, and this can simplify to some extent as x minus 1 factorial all over k minus 1 factorial times x minus k factorial times p, look at that, p got multiplied there, to the k, and q to the x minus k, right, because we're getting rid of the 1 there, and hey, there we go, that's where our formula came from. So now let's go ahead and work another problem, and that is the probability that a person living in a certain city owns a dog is estimated to be 0.3. So find the probability that the 10th person randomly interviewed in that city is the 5th person to own a dog. So if we do that, we're going to say that, well, let's see, this looks to me like it's going to be using the negative binomial. And why is that? It's probably because, well, first off, the experiment consists of a number of repeated trials. Each one of those trials has just two possible outcomes. That is, a person either owns a dog or they don't own a dog. Probability of success is the same thing. We're going to call owning a dog as a success. And the trials are independent. People, if one person owns a dog, it doesn't really affect probably who the next person we run into, whether they own a dog. And we're going to continue this experiment until we get a fixed number of successes, and that is that the 5th person, or it's going to be the 5th one to own a dog. So we're going to use negative binomial, and in essence a binomial distribution of x, k, and p. So what is the x going to be? Well, clearly it's going to be 10. And k is 5, the 5th person, and the probability is 0.3. Oops, 3. Hurry, count up 3. Okay, so if that's the case, then we'll say a binomial of 10, 5, and 0.3 is equal to, remember that we're going to write this out at, okay, just this one time I'm going to beat it to death so you see every little detail. It will be, I keep losing my pen there, okay, it's going to be x minus 1 factorial over k minus 1 times x minus k factorial p to the k, q to the x minus k. And so if that's the case, we'll have, let's see, x is 10, so x minus 1, this is going to be 9, basically 9, and then k minus 1, it's going to be 4, so it'll be 9 choose 4, and then p is 0.3 to the 5, that's k, and q is 0.7 to the 5. So there we go. Now, we do have one special case, and that is the case where we have something like exactly like this, but let's say it's you run into the first person to own a dog. You can see it's pretty clear you would use the negative binomial distribution, but you'd be plugging in k is equal to 1. If you do that plugging in where k is equal to 1, it simplifies everything quite a bit. In fact, this whole formula, it simplifies to something that looks simply like this. For k is equal to 1, the negative binomial distribution becomes what we call the geometric distribution. It's the same thing, it's just for the simplest possible case, and that is just p times q to the x minus 1. So let's look at all the distributions we have so far. We've got binomial, okay, and negative binomial, and geometric. And we haven't really, we did a problem with negative binomial. We didn't do one with geometric, but you can see it's probably going to be even simpler. It's the same as negative binomial, but it's even simpler. So let's look at that. The probability, for example, that a student is going to pass a written test for a private pilot's license is 0.7. Probably if it was me, it'd be like 0.2, maybe less. You don't want me to pilot your plane. Find the probability that a student will pass the test on the first try. Now remember, they're passing the test. It may be on the second try, the third try, but basically you are looking for a pass, a try on, so you're saying, it's kind of like saying, I'm going to flip coins until I get a head, right? So I get a tail, a tail, a tail, and then I get a head. Oh, I'm getting a success. This problem is very much like that. First we're saying, oh, we flip it, and what's the chance we'll get heads on the first time? Well, you know, there's a certain probability in this case. What's the chance I'll get heads on the second time? What is it I'll get it on the third try? What's the chance that of all of these three added together? Well, let's calculate things out. If it's on the first try, then essentially we'll use that geometric distribution. We're saying we'll want it to be a success on the very first try, and that will be what? P is 0.7 and Q is 0.3, and X minus 1, well, 1 minus 1 is 0. So it turns out to just be 0.7. Chances that we're going to pass it on the first time is 0.7. How about second try? Well, that's going to be 0.7 times 0.3 to the second try, so it's going to be 2 minus 1, so it'll be 1, and that is 0.21. Third try is going to be 0.7 times 0.3 squared, and that's 0.63. So you can see chances are pretty good you'll get it on the first try. If you don't get it then, you know, chances are good you'll get it on the second. By the time you, oops, let's put a little 0 in there. There, that's better. 0.063. It's starting to get smaller. And before the third try just means add A and B together. So it'll be 0.7 plus 0.21 is 0.91. So nothing too bad. Now, let's see. Now we want to see the probability that a CNC lathe makes a defective part. It's 0.02 for any part made by the lathe. Determine the probability that this lathe makes 22 parts, and they're good, and on the 23rd it makes 22 parts. 2 of them have to be bad somewhere in there. And on the 23rd part, there's going to be the 3rd defective part is produced. So again, this is clearly going to be something that is a negative binomial sort of problem. We've got X is 23 different trials that we're going to have. We want K of them, which is 3, to be bad. The probability of producing a bad part, that's a success in some sense, is 0.02. And of course that means that Q is 1 minus 0.02 is equal to 0.98. Okay, let's just take it and plug it right in to the negative binomial. We'll say it's 23 minus 1 factorial over 3 minus 1 factorial. That's 23 minus 3 factorial. And take that, multiply it all out, 0.02 to the 3rd, and then 0.98 to the 23 minus 3, and that's 0.001. Not bad. Okay, got that. Now let's move on. We can say that the expected value and variance for that negative binomial distribution are just going to be, the expected value is K divided by P, and again your book has a very nice derivation of that. And the variance associated with this is just going to be K times Q over P squared.